This question is about the reactions of compounds with more than one functional group. A chemist investigates some of the reactions of compound L as shown in the flowchart below. Complete the flowchart by showing the missing organic structures in the boxes. Okay, so let me just zoom out a little bit so we can see the whole question in one place. Okay, and get my clamps down in there as well. There we go. So there's the full synthesis route. So we'll need to try and build it up bit by bit. I'll zoom back in a second. Okay, but you can see this type of question is going to be an examiner's favourite for the organic papers. All right, they like trying to test you out in these synthesis routes and see if you can follow the patterns through. So looking at the functional groups, looking at where they are, and thinking about what will happen based on the conditions that they're reacting in. Okay, so let's zoom back into the middle section, and let's focus on that one there. So let's start here. C6H5, so there's a benzene ring here, they're just giving you the molecular formula. We've got a double bond, there's an alkene there, C double bond OH, there's a carboxylic acid. So I'm reacting this molecule with HBr. So this is the key with synthesis. You've got to be able to remember what your functional groups react with, and then what would be formed. So our alkene will be able to react with the HBr, okay, because we get an electrophilic addition reaction taking place between these two. There's going to be no reaction between the carboxylic acid and the HBr. They're both acidic products. There's nothing going to happen there. Okay, so reaction one, the HBr is going to react with the alkene section of the molecule. So your product would look like this. So there's no change on the carboxylic acid. The HBr is going to act as an electrophile. Therefore, the double bond will break. And you've got to think now, well, where is the HBr going to go? Where's the H going to go and where's the Br going to go? Let's put the C6H5 back in there for a second. And this is where you've got to look at the question in its entirety. If you go back down to the bottom, you can see here, whatever this is going to react with is going to end up with an OH. Now, if you look at compare the molecules here, okay, the OH is on this carbon. Okay, the carboxylic acid hasn't changed. So in that case, the bromine that's going to be added to the molecule from here will be going on that carbon there, because that's what's going to change in the reaction, in the next reaction, to produce the OH over here. So watch out for that. Okay, so there is your first compound. Don't worry about any names for it. It just looks like that. So you can see the only change is the double bond has gone. I've added the bromine onto which is the third carbon. Okay. So the second bit to this, I'm reacting this molecule with sodium hydroxide. Now again, my sodium hydroxide is going to react with the bromine section, the OH, the hydroxide ion is going to react with the bromine because they've got a haloalkane here, and we've got a nucleophile, so there's going to be nucleophilic substitution. So what's going to happen is this. I'm going to get the OH swapping places with the bromine, hence the reason why I've got the OH here on the molecule now. All right, the C6H5 will stay where it is, but something funny will happen here. This is a carboxylic acid, this is a base, and acid and base always makes a salt. So what will happen is the H from the OH section of the carboxylic acid will be dropped, and that will become a negative charged ion. And actually what happens is it's forming a salt with the sodium from the sodium hydroxide. So you would get a sodium ethoxide ion in essence there. Okay, but the examiner's only looking for the idea that the carboxylic acid and the base react in that way. So you can get away with just putting the O minus there. And the hydroxide then has replaced the bromine. So the main reaction for the synthesis is the hydroxide ion replacing the bromine, the haloalkane becoming an alcohol. This bit here is to do with an acid-base reaction. So the C double bond OH becoming the O minus is to do with the acid-base reaction. Now if we go the other way, we're going to be taking this haloalkane and the carboxylic acid and reacting it with ammonia. So in this one, the ammonia is going to react again with the haloalkane, and that reaction produces an amine. The haloalkane with ammonia in excess ethanol produces an amine. So 1, 2, 3, OOH, and we'd get NH2 there, C6H5. Now again, you could have the ammonia reacting with the carboxylic acid and producing an O minus. and that can happen, but they're both weak. This is a weak base, this is a weak acid, so it doesn't always happen. But it wouldn't be wrong if you put an O- there.